Welcome to the first video in the electrochemistry unit. This video is going to be about electrochemistry, what it is, how chemical reactions can be used to create electricity, and then we're going to start to look at the first electrochemical cell called Voltaic cells. Electrochemistry is all in chapter 20 of your book, but it's actually going to start in section 20.3 because 20.1 and 20.2 were oxidation reduction that we've already looked at. So just to review, remember that oxidation is a loss of electrons, which means your oxidation number is going to become more positive, and the reducing agent is actually what undergoes oxidation. And then reduction, that process means you gain electrons, which means your oxidation number is going to go down because it's becoming more negative, and the oxidizing agent is actually what undergoes reduction. Remember, the agents are what just help in the other process, so they actually undergo oxidation and reduction respectively. The reason that you need to know oxidation and reduction still is because electrochemistry is all about using redox reactions to create electricity. So electrochemistry, this is the study of the relationship between chemistry and electricity. It includes the study of both spontaneous and non-spontaneous processes, and we're going to look at both. We're going to look at both within the two electrochemical cells. An electrochemical cell is simply a device in which chemical energy from chemical reactions is changed to electrical energy through the process of work. The first type of electrochemical cell is a voltaic or a galvanic cell. These are the same thing. You might just see these two names used for the same device. So a voltaic cell uses a spontaneous chemical reaction, and it has to be redox. It uses a chemical redox reaction to generate electricity. Very common example is a battery. It happens on its own. That's why we use batteries. The electrons are transferred in a voltaic cell spontaneously, so energy is released. This energy is able to do electrical work, which is electricity. And the electrons are actually transferred through a wire in a voltaic cell. Then we have what's called an electrolytic cell. The electrolytic cell actually uses electricity to make a non-spontaneous reaction occur. So electrolytic cells are non-spontaneous. You have to actually put work in to get that to work. And this drives a normally thermodynamically unfavorable reaction. So think about delta G. Delta G would be positive. And so you use electricity to make a non-spontaneous reaction work. Now when we're talking about spontaneity again, remember that a spontaneous reaction is spontaneous no matter what. So it doesn't matter if the reactants are in direct contact, like this picture on the left. Notice that the metal is dipped into this copper sulfate solution, or it can be spontaneous if they're connected through separate compartments. So notice here we have two different beakers, but it's still spontaneous because we're still producing electricity. So voltaic cells, this is what we're going to focus on in this video. Voltaic cell is spontaneous. That's the first thing that you need to know. And the electrons are transferred spontaneously from the anode to the cathode. We're going to talk about what these are, but it's through an external circuit, like a wire. So here is a picture of a voltaic cell, and we're actually going to break this down so that you know how to make your own voltaic cell. So when these electrons are transferred from the anode to the cathode, energy is released. This energy is actually what we can use to make electricity, and that's why this light bulb lights up. And as the electrons flow through this wire, that is electric current. Electrons flowing through a wire create an electric current. And so here we have half reactions happening, right? We have zinc oxidizing, we have copper 2+ being reduced. So in a voltaic cell, the chemical reactions are redox reactions. In this voltaic cell down here, we have two different compartments. We have one called the cathode, that's the one on the right here. The cathode is the electrode, so an electrode is usually a piece of carbon. It's the electrode where reduction occurs. So reduction always occurs in the cathode compartment. Then we have the anode. The anode is the electrode where oxidation occurs. So you always have two compartments in a voltaic cell. You have a cathode where reduction occurs and an anode where oxidation occurs. Now, after a period of time, It's very important, so write this down in your notes. After a period of time, the cathode may appear larger. And the reason that it appears larger or it has more mass is because the ions from the solution, notice in this picture, the ions from the solution are actually plating onto this electrode. That just means that as it becomes copper metal, it needs somewhere to stick, and it's actually going to stick onto the electrode. And then the anode actually may appear to become smaller, or it may lose mass, because notice that the zinc is actually coming off into solution. So it's becoming an ion and it's falling into solution, because remember, ions have to be in solution. And then always remember that electrons travel from the anode to the cathode. Think about alphabetical order, from A to C. So electrons travel, that's right here, from the anode to the cathode. So to remember anode and cathode, oxidation occurs at the anode, reduction occurs at the cathode. So you can remember red cat, right? Red cat, reduction at the cathode. Or if you're someone that just wants to remember it using vowels, A and O, anode oxidation, both start with vowels. C and R, both start with consonants. But you have to remember what occurs where. Okay, so again, remember the red cat. So now we're going to actually break down this picture, and we're going to look at how a voltaic cell works. So step one, electrons are produced by oxidation. Okay, oxidation, this is the anode. So we have zinc metal, that's one electrode. We have copper metal, that's the other electrode. You always have metal or you'll have carbon as the electrodes. In this case, we're going to have two pieces of metal because that's actually what is being oxidized and what is being reduced. So electrons are produced by oxidation. We need half reactions at each electrode. So anode tells us this is being oxidized. So we're going from zinc to zinc 2+. Zinc can only have one charge. So we're going zinc to zinc 2+ plus 2 electrons. Then the electrons move through the external circuit. As this zinc loses electrons, it's going to flow through the wire from the anode to the cathode. And then the electrons are used at the cathode to reduce the copper. So copper is going from Cu2+ to Cu. So it's going to actually plate onto this copper sheet. It's going to actually appear larger. So electrons are produced through oxidation. It flows through the wire. It creates an electric current. Then we have reduction occurring at the cathode. And then to complete the circuit, ions have to actually move within this cell. So just to kind of summarize what we looked at in this slide before we talk about how ions move. Electrons leave the anode, they flow through the wire to the cathode. As the electrons leave the anode, and the cations that are formed, these zinc 2+, dissolve into the solution, and then as the electrons reach the cathode, this is now more negatively charged, so the Cu2+ is attracted to that. Okay? So cations are attracted to the now negative cathode, and then the cations gain the electrons and they're deposited onto the metal cathode. So we talked about ions needing to be able to flow. So we have the positive ions collecting around the zinc anode because we have all these Zn2+ ions, and these the copper solution doesn't have as many ions now, and we can't have charged solutions. Right? Our solutions need to actually remain neutral. So these solutions need to actually remain neutral. So we have to actually have ions flowing in order to keep this neutral. The reason that these need to stay neutral is because if the charges aren't balanced, the flow of electrons is going to stop. So we need these solutions themselves to stay neutral, so that way the electrons continue to flow. So what we actually use to keep everything neutral is we use what's called a salt bridge. So the movement of ions occur through a salt bridge, which is usually an inverted U-shaped tube that contains some sort of salt solution. And what it has is some sort of porous disc or a porous membrane to allow anions and cations to flow. So the ions of the salt don't interfere with the reaction. Okay? The ions simply make it neutral. So the positive ions, the cations, move toward the cathode, right? Cat and cat. So positive ions move toward the cathode, negative ions, or the anions, move toward the anode. Okay? And this is because when electrons flow, charges aren't balanced. So a salt bridge usually contains some sort of salt solution, maybe potassium nitrate. to keep the charges balanced. And so the salt bridge allows us to keep neutrality. When you create a salt bridge, you want to make sure that you use a salt that will not precipitate, like potassium nitrate or sodium nitrate. You want ions that are always soluble. Okay, so these just show different pictures of voltaic cells. Notice they all can be represented a little bit differently. Here we have a salt bridge, the inverted U shape. Here we just have a porous membrane or a porous disc. They both work. They both allow cations and anions to flow. It depends on what you have. Now notice down here the picture of the anode versus the cathode. Notice the anode has lost mass. The cathode has gained mass. And what we'll do is we'll look at some animations in class as we look at the inner workings of a voltaic cell. So just to summarize, electrons always flow from the anode to the cathode. Notice that they're on different sides here. We have the anode on the left, cathode on the right down here, but at the top, anode is actually on the right. So it's very important that you make sure you notice which electrode is where. Typically, when you create a voltaic cell, typically you're going to put the anode on the left, the cathode on the right, but it's important that you can still distinguish between the two. And then notice here in each one of these pictures we have a voltmeter. A voltmeter just measures the potential of the cell. So some mnemonic devices to remember information about voltaic cells, because sometimes this is easier. You can remember an-ox. So oxidation occurs at the anode. It also shows mass decrease. Red cat, reduction occurs at the cathode. It will increase in mass. So you're going to have to figure out how to remember that anode decreases, cathode increases. Or you can remember fat cat. Electrons flow from the anode to the cathode. And then you can remember cathode. The cathode is actually what is positive in voltaic cells because the T looks like a plus sign, which means the anode is negative. So these are just some ways for you to remember all of the different things about voltaic cells, and then in class we're actually going to look at writing half reactions and representing the voltaic cell.